Greetings and welcome to a new video. In this video we will discuss the power factor correction in a three-phase circuit having a balanced RL load. So we will see an inductive load action. We will see how we can create our capacitive corrections in order to get a specific power factor. So let's look at our objective. You see here the circuit, which is a three-phase circuit. You see here three sources and the values are shown here. So actually each of them has 100 volts peak. And the frequency is here 60 Hertz, and you see also the sequence ABC. So you have for each of them that the phase is 120 degrees out of phase in this sequence. The balanced load will be a series RL load, also shown here. It is also in the star connection. And you see here 20 ohms and 50 millihenries in each load here. We like to have a power factor which is corrected to 0.8 lagging. In the second case, we will also look at for a unity and then compare actually the result and also what the effect is of getting a unity. Before we dive into the calculations in detail, let's also designate here our omega, which is this 2 pi times 60 Hertz, which is then in this case approximately very close to 377 radians per second. Okay, let's first look at our calculations. Now, using a three-phase circuit, it's helpful to look at what we call the per phase equivalent circuits. In this case, we have a balanced load. That means this node and that node is actually virtually connected to each other. So we can assume that the VA voltage source will be across the resistor and the inductor combination here in series. So we can take that out and carry out our calculations just looking at that part of the circuit. And we also convert our time domain representation and the frequency domain representation using the phases. So we see here the 100 and the phase of 0 degrees. Again, our resistor and inductor values are shown here. So we can say first our load impedance, just this part, is then the series combination of the resistor and the reactance of our inductor. And that's shown here. So you see this load impedance is R plus J X of L, which is our reactance of our inductor. And that is then J omega L for this part. And when you substitute here the omega and the resistor and the inductor value, you get here 20 plus J 18.85 ohms. Now from here we can calculate actually the impedance angle. That can be done by imaginary value divided by the real value and then take the arctangent of that one. That will create a specific power factor. Now we will of course want to improve that to get to 0.8 lagging. Now we can do that. That is another example we have carried out where we have applied a parallel capacitor. So this is also shown here. So we can from here go to here and then add here the capacitor to be determined to get a better power factor. So when you look at that, then we can say the power factor correction formula can be then used, which calculates actually the reactance of this element to correct the power factor of the load to a specific value, in this case 0.8 lagging, and the next time to unity. And that formula is shown here. So that is then here x1, which is then the element to be determined, is equal to this r squared plus x squared. I will explain shortly what it all means, divided by r times the tangent of the arc cosine of this PFC, which is the corrected power factor, and the minus x squared. Now in here, the R and the X are real and imaginary parts of our load impedance. So this is actually this is the R and this is the X, just 18.85. Before the power factor is corrected, and the power factor correction, so the PFC, is what we need. And then when you substitute here the values, in this case for a specific situation, we can calculate the reactance X1, and from there we can calculate what the required capacitor is. Now, then you have here the situation where this circuit is then converted to a circuit where you have here parallel capacitors for each part of the load. Okay, this is by the way one configuration. We will see also another configuration and also compare the results. Okay, now let's calculate now this X1 for a specific power factor of 0.8 lagging. So what should it be? Now you can calculate that, just substitute here the 20, here 18.85, and then 20 times the tangent of arc cosine of 0.8, that's this first part, and minus again this x squared, which is 18.85 squared. you will get here approximately minus 196.2 ohms. Now you see the value is, or the answer is negative. That indicates actually that you need a capacitive element. Of course, I said already that you need a capacitor here, but you can already see from the answer of X1 that you need a capacitive element. So if this was a positive value, we need an inductive value. So the X1 is a reactance, but it is, for this case, also the reactance what we need for a Y-connected or star-connected equivalent capacitors. This is an important note. We'll come back to this shortly. So then we can write the following. We can say, since this is a capacitor, we already have concluded that we can say X of C is equal to X of 1 absolute value, and that will be then 196.206 ohms. And we also know that X of C, that is our reactance, is equal to 1 over the omega of C, and then we get the C here is equal to 1 over omega times this X of C. Now when you substitute the omega, which is here from the expression of the sources, and our required X1, absolute value of that one, you get here 13.519 microfarads. So this is the capacitor we need in each load parallel. So here, in here, and here X we have shown here. Similarly, we can do that for the power factor 1. So what happens then? Well, use again the same formula, and then just change this 0.8 to 1. The rest is exact same. Then you get here minus 40.07 ohms. So you actually have reduced your reactance. What does it mean for our capacitor? Well, we use again our same formula. Then we can say the X of C is equal to X of 1, X1, because that's the absolute value. And then you can use this formula and then convert that to get the capacitor. In this case, the capacitor is now larger, so you need 66.2, so 66.2 microfarads. So that has increased actually in this case. So if you want a better power factor, you have to also use a larger capacitor. Okay, that's the conclusion, and we actually have made now the job for first part, for 0.8 lagging and a unity. All right. Well, we can also look at a different form, different configuration, because this is the power factor correction with the Y-connected capacitors that's actually shown here. So we have calculated this for two cases, 0.8 lagging power factor and unity. So these are the results for our calculations. But we can also have the capacitor in a different configuration to compensate or make the power factor 0.8 lagging and unity. So this X1 what we have calculated for this specific 0.8 lagging power factor is the reactance of the Y-connected equivalent capacitors. Why is it Y-connected? You can see here this capacitor and these three capacitors are actually in the Y connection as we have it also for our loads. So in order to go to another configuration which is called delta here, we can also make this configuration. So we can actually place the capacitors between the loads here. And again, another capacitor like so. This is another option. So what is then the benefit of doing this? And what is the difference actually compared to the other configuration? Now, well, we have to make the conversion from our Y-connected equivalent circuits or equivalent capacitors to the delta connected equivalent capacitors. Now that is done by looking at the delta and the Y connections, and that is the formula, famous formula you know. If all the impedance are exact same, you get that the delta impedance must be then 3 times the Y impedance. That means the reactance, what we have calculated here, for example this, must be then 3 times larger. So we have then the Z delta must be then 3 times this 196.206. That is then this value. And now we can again use that to calculate the capacitor for that configuration. So actually this capacitor, and also this capacitor. They're of course all the same. Now, we have now a new reactance X of C, which is then the Z delta, which is 588.618 ohms. Again, you use the formula for the reactance of the capacitor, so 1 over the omega C, and then rewrite this, so you get the C is equal to this. And now use the formula, or the value, new value for our reactance. And that will give you 4.5065 microfarads. In this case, you see actually the power factor of 0.8 lagging. In order to get that, in this Y-connected configuration was 30.5 microfarads. And now we have this much, which is 4.5 microfarads. I actually have reduced this by 3 times because the impedance is also going up by 3 times. Now, we can do that also similarly for the power factor of 1, and that is then 22.066 microfarads. So you see now 2 configurations to make this power factor correction, and you actually see also the changes or also the reduction in our required capacitors. Okay, let's make the summary here. You see actually here now the full picture, power factor correction with the Y-connected capacitors and power factor correction with the delta-connected capacitors. Again, you see here the comparison of the capacitor values between these 2 configurations. Again, it depends on what is beneficial and what is then more practical in the system you are working on. Okay, let's bring it here and look at our simulation results. This is for the simulation for a power factor of 0.8 lagging. You see the original circuit in the SPICE simulator where there is no correction, so there's no capacitor. Here we have the power factor correction with the Y-connected capacitor. You see actually this here. And this is now the power factor correction with the delta-connected capacitors. You see actually that's shown here. What you also see here is for the first case that the phase of the source A, IA, IB, and IC are actually here shown. So the phase of VA was 0, but the source current here has a phase of almost minus 43 degrees. So you see this is a lagging because the current here, the source current, is negative, so it is lagging the source voltage. You can also of course calculate it from the impedance angle using the resistor and the reactance of the inductor here. Now you can also look at the power, so these are the real powers, they are all the same, so 132.4 watts approximately, and it's also for each case the same. Now what is actually changing? Well, you can look actually in this table also. You see the phase, again, 43.034, that's actually from here. So it is lagging, and also the power factor is given here is 0. Actually it's 728 milli, so it is actually 0.728. In the next version, which is actually this correction using a parallel capacitor, you see the power factor is indeed 0.8, so 800 milli, and the phase is here given as we have calculated. Now, you also see that the source current has reduced, so it was here before 3.64, let's say approximately here 3.31. That is of course an improvement in terms of power dissipation. And you see also that the same result will be then for the delta connected capacitors, where you see here again here 0.8 for the power factor and the same phase and exact same source current. So it depends on, again, what you require or what you prefer in our configuration, but the end result is exact same in terms of the power factor. Okay, so it's all according to calculation, so we can say this is nice. Let's also look at the situation for power factor of 1. What we observe first is that the phase of our source current is now 0 degrees for this IA, and that is also in phase with the VA because the VA phase was 0 degrees. You also see that the source current has decreased. It is now 2.65 amps, and here it was 3.64 amps, and it was before with the 0.8 power factor, 0.8 lagging, it was here in this case 3.31. So the source current has reduced if you improve your power factor. What you also see is that the power is exact same as before, the real powers for each branch of the loads. In addition, the phase here at IB and IC is also in phase with the VB and the VC. So there is no phase difference between the currents and the voltages. If you look at the table, you see indeed the phase is 0 degrees and the power factor is 1. What you also see here, that's for the power factor correction with the delta connected capacitors, that again the real powers are exact same for each phase, and the same current is also here in the phase currents, and again the phases are exactly in phase with the sources. So the phase of the currents are in phase with the source voltages. And also the result here, phase of 0 and a power factor of 1. So our end result for both configurations is that we get a power factor of 1, but using, of course, in this configuration, the Y connected configuration, we need a 3 times larger capacitor. All right, that was our example considering a 3-phase circuit having an RL load balanced in the star connection. And we have looked at how we can determine the required capacitive element to correct our power factor, in this case to 0.8 lagging, and also the unity. And we also compared the results for 2 configurations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.